Hola amigos! Welcome to the third and final chapter of this volumetrics rendering course. Today, we're going to learn how to edit the type of pseudo-volume textures that we have been using, and we will do it in runtime, so you can make gameplay effects like bullets piercing through a cloud volume and things like that, like this type of effects. And as a bonus, we will add some animated noise to improve the visuals of our cloud rendering. Let's get started. Here's our little volumetric cloud, just as we saw it at the end of the last video. We're going to start by creating an instance of this material so we can change some of its parameters. We can leave the default name. And before we do any changes, let's also create a new texture, render target. And I'm going to call this one RT and maybe ball texture. Now let's increase the size of this. We want to store a bunch of different frames, so maybe 2048 square is a good size. And now we can change the format maybe to RTF16 float, so we just store one channel. And now we can save, close this, and open or maybe assign our material instance to this one. Right now we haven't changed any parameters, so the cloud looks the same. But let's go into our material instance and replace our volume texture by the render target that we just made. So we can drag and drop it. And if we save, our little cloud sadly is gone. So next, let's see how we can paint something on this texture. We're going to need a material to paint on that render target, and that material somehow needs to generate these slices of a volume and put displaying in frames. Now, a key part of this material is a function to convert from UV to a 3D position. And we'll do that a few times, so instead of copying a bunch of nodes over and over, let's create a material function. So material function, and we can call this one maybe UV to 3D. Now let's open it up. And okay, we'll need a couple inputs. So function input, and we'll need two of those. The first one obviously is going to be a vector2, and let's call this UV position. And by default, and for the preview, we can just grab the texture coordinate. I'm going to change this into a plane. And for the second parameter, we will need just a scalar, and we need to know the number of frames, so XY frames. Now you can convert this into a vector2 if you want to have different number of frames on X and Y, but for all of the examples that we've been using, we have the same number of frames on both axes, so I'm going to keep it like this. And let's also create constant for the preview, and maybe say I think it's 12 on our textures. So now we have these two inputs. Now if we multiply these two, let me output the result. Now our texture, instead of going from 0 to 1, goes from 0, in this case, to 12 on both axes. Now let's break out those components, and first let's take the fractional part of each. And because we start to have more than one component, let's make a float 3. Now let's get the X component here, the Y component, and let's connect this make float to the output. And now we have our XY coordinates or texture coordinates for each one of the frames. Perfect. We just need the Z component now. And for that, we're going to need the floor of this number on both components, obviously. Now, if these values are going 0 to 1, 0 to 1 over and over, the floor goes 0, 1, 2, 3, 4, and so on. So this is the X index of these cells, and this is the Y index, right? So now we just need to multiply the Y index by the number of frames, and then add the X index. And now we have the index of this cell from 0 to 144. Now if we divide this by the number of frames multiplied by itself, so if we divide this by 144, now our Z index goes from 0 to doing this all the way to 1. And that's our Z coordinate. And there we have it. We just create a function that can get a UV coordinate input and will return a 3D position in a 0 to 1 cube. Perfect. Let's apply and save. And now select anything, or don't select anything, sorry, on the graph. And here we'll choose expose to library and check this. So we can access now this function from the context menu. And now we're ready to create our painter material. Actually, let's go back to our function for a moment, because I realized that in most cases we might want the coordinates to be centered on the cube instead of going from 0 to 1, they go from -1 to 0 to 1 on each axis. So that's an easy change. We just need to multiply by 2 and then subtract 1. And there we have it. They are centered now on the Z axis and both on X and Y. X and Y. And all these values here, all the black stuff, and from here to there are negative. So let's apply and save. And now we can create our material. So material, and let's call this one material volume painter. Okay, let's start by changing the shading model to unlit, because we only care about the final color. So we can use the emissive color, and let's create a few scalar parameters. So we're going to need the number of frames per side. Let's default this to 12. The texture coordinates, and then our new UV to 3D function. And let's connect each input, and now we can take the length of this vector. Let's output it for a moment, and you can see that on each square it goes from 0 to 1. And now let's add a subtract and a new scalar parameter. We can call this radius. Let's give it a 0.5 default, and then subtract the length from the radius. And now we have something that looks like a sphere in a pseudo volume texture with a maximum radius of 0.5. Perfect. Now, one of the problems is that when we subtract it, now our gradient goes from 0 to 5 to 0, from 0 to 5 to 0. And we might want instead to keep the full 1 to 0 range. So let's divide this by our radius again. And then we can saturate this to eliminate all the negative values. And then finally, let's add a multiply and add another scalar parameter for the density. Maybe 1 by default, so it shouldn't change. But now we can change the density, and our result fades. Oh. And we can change the radius. Perfect. Now we need to paint now this into a render target, and for that we're going to need a small blueprint. Let's create a new blueprint of the actor type, and we can call this one BP volume painter. Let's open it up and go to the event graph, and let's create a new function, and let's call for now debug paint. Let's do it properly. Debug paint sphere. And we'll need a new variable, RT for render target. And let's search for render target. And we need a texture render target to the object reference. Now we can compile and save and open the content browser and drag our render target texture to the default value of this blueprint. Now let's get a copy or a reference to our render target and search for begin draw canvas to render target. We'll start painting on this texture and search for draw, and we'll need a draw material. The material that we want to draw is our volume painter material, so we can drag it from here to our render material. And let's also connect the size from the begin draw canvas to the screen size on our draw material. And after that, we can drag from the context and search for end, which will give us end draw canvas to render target. And I think that's correct. Let's actually make sure that our function can be called from the editor. Now we can compile and save, go back to our viewport, and let's drag one of these blueprints to the scene, put it here, and click debug paint sphere. Bam! And there we have it. So now if we go back to our material and let's change the radius to 0.5 and maybe the density also to 0.1, and click debug paint, we should have a sphere half of the size and less dense. Yeah, that's pretty cool. Let's say what else we can do with this. Going back to our painter material, we've seen how to change the radius and the density of the sphere that we painted inside the volume. But if we want to change the position, we'll need to modify this vector that we're using to calculate the length. We can do that by subtracting the center of the sphere, the center position of the sphere. So let's add a new vector parameter. We can call this one sphere center and connect the RGB output to the subtract and the subtract to the length. Now if we modify this parameter, X will move the sphere left and right, Y up and down, and B or blue will move the sphere in the Z axis, so the entire thing will shift. So let's say that we want to paint half a sphere. So -1 is down on the Z axis. So click on our volume painter, paint a sphere, and now we have a sphere. Cool. Now this is pretty fun and all, but it's kind of annoying to keep changing these values by hand and then have to reapply and then go back to the viewport and do this thing over and over. So let's go back to our blueprint and figure out a better way to pass the parameters to this material. The easiest interface would probably be to use something like a brush coming from the camera in the direction that we're aiming to paint inside our volume. And to do that, we'll need our volume painter to be able to receive input. And we could add a movement controller and all that, but it would be a lot easier to just go to the class settings and change the parent class from actor to default pawn. Now this has a collision component, mesh component, and movement component. So let's compile and save, and we can see now our volume has a sphere to represent, our volume painter has a sphere to represent the actor. And if we scroll down to the auto possess player, we can change this from disable to player 0. So when we press play, we are the volume painter now. Excellent. Let's open it up again and add our first function that is not a debug function. We can call this one reset RT. And this will clear the canvas and empty the volume. So let's get a reference to our render target and just search for clear and select the clear render target to the node. And if we keep the clear color as black, this will just empty our volume. Don't forget to click or select enable call in editor. So we have a button here that will allow us to remove a sphere or add it again. Perfect. Now we can save and move on to the next step. One thing that we need for our painter is to specify which mesh are we painted on. So let's open it up and add a new variable of the type static mesh actor object reference. We can call this one target volume mesh. And we need to make this public so we can edit it outside and either select an actor from the scene or from the viewport, or just select it from the drop box since we don't have a lot, and it's this box. Now one thing that we're going to need as well is to be able to see this box. If we reset the volume field, we have an empty box and it will be hard to know where the volume is or where the bounding box is. So let's save everything and create a new function that we can call maybe update traces. Let's create a new boolean and call it maybe show guides. Let's give it a default value true and make it public also. So if we show the guides, then we're going to draw the bug box. Now the center of that box will be the position of our target volume mesh. So get actor location. That's gonna be our center. Let's move this up here maybe. Now from this we can also get the actor scale. And since I know that our cube at a scale of 1 measures 100 units per side, then let's multiply this by a float and multiply it times 50. And that's half of its size. So let's put that on the extend. And that would work. Let's give this maybe a bright red color. But if we rotate our box, that is gonna fail. So let's also get the actor rotation and plug this into our rotation. And now let's see if we compile and save and press play. Now we can see our box. And oh, I don't think it's set to movable, so if we scale it and rotate it, the box is still displayed properly. Excellent. Let's undo these changes. Perfect. And go back to our painter. Next, let's define a point to trace. So let's create a new float variable for trace distance. We can call it that, trace distance. And that point is going to be the actor location, so the painter's location, plus some offset. So add another vector. Now this offset is going to be based on the direction we are facing, so we need the actor forward, and then we'll multiply this before adding it. So let's grab our trace distance and replace this by a float, connect it there, and connect this here. Now we can also compile this and give this maybe 1000 units default value, and this is going to be the point that we are going to sample. So just for now, let's draw a sphere. Debug a sphere at that location, and maybe also red. Let's compile and save and see if it works. So at first glance, it seems to be working. We can move the camera and the sphere moves in front of us. But if we rotate the camera, there is some problem here. And now is where I realized that since I'm inheriting from the default pawn, this movement controller is not using the pitch or the yaw or the roll of the camera. But in our case, we care only about pitch and yaw. So enable those, go back, give it a try, and now it's working. Now we just need to check if the center of this sphere is inside of the cube. There are a few ways to know if a point is inside a box, but conveniently for us, Unreal has a function called testPointInsideBox, which needs a point and a box, and will return a boolean called isInside. It's pretty self-explanatory. However, this assumes that the box is aligned with the world axis, and as we saw, we might have transformed our volume mesh and rotated it, and which means that we cannot use that box or that bounding box. The alternative is convert this point to the local space of our volume mesh. So let's do that by first getting the transform of this actor. So get actor transform, and then we need to do an inverse transform. So search for inverse, and we need the inverse transform location, since we are transforming a position. Now let's drag this here and maybe add a couple reroutes to make things a bit nicer. Now that's the point that we want to test, and now we just need to make a box that represents this volume mesh at a scale of 1. So we can make a box from center extents, and the center is at 0, 0, 0 in the local space of the mesh, and the extents are 50, which is half of the mesh size. Now, to see if it works, we can branch this based on this is inside return out or output, and if it's true, we'll draw a sphere. If it's false, we'll draw a slightly different sphere. So if it's true, we'll paint it green. If it's false, we'll paint it red. Now we need to also plug the trace point into the center input of this, and I'm going to also change the radius to 50. So with a scale of 1, our brush will cover the entire volume. So let's transform this a little bit and see if this works. So we have our sphere, and yeah, and it seems to be working. Excellent. So now we know if we are able to paint or not. And it might be still tricky to guess the depth. So maybe I'll add later some crosshairs or again some kind of axis guides to help visualization. Now we can undo these transformations now that we know that it works, and go back to our blueprint. Let's add a couple more variables to our blueprint. First, we'll need a float for the paint radius, which we can get here, and instead of having a radius of 50 or 300 or whatever, let's keep our values smaller and then multiply after they are defined. So let's add a multiply times 50 and then connect this to our debug sphere. Now we'll give it a default value of 1, and let's also create or make it public and create a boolean to store the result of the test. So we can call this valid paint position, and a vector to store that valid position. So paint position. We can set this one here. So after we paint our debug box, we'll set that to the result of the test, and then we can compare the branch with that value. Now we'll set this position only if it's true. So if we paint the green sphere, then we'll save that position. However, that position right now goes from -1 to 1, or sorry, -50 to 50, because that's the extent of the box. So let's divide that by 50. We can change this into a float, set it to 50, and there we have it. Now these two don't need to be public, and now we can compile and save. And let's go back to our debug paint sphere function, and actually let's just change this one and the name on this one to just paint volume. Actually, before we make any changes to our paint volume function, let's go back to the event graph, and on the begin play event, let's create a dynamic material instance. Create dynamic material instance. The reason is that we are going to pass parameters to this material that we created earlier, so we need to create a dynamic material instance to be able to change those in runtime. So parent, let's search for volume painter material, and then we can promote this to a variable. Let's rename this maybe dynamic material instance volume paint. Compile and save, and now we can go back to our paint volume, and first we want to replace this render material by our new instance. Now before we use that, we need to, or before we draw it, we'll need to set the parameters on this material. So they are called sphere center and radius. We can set the density as well. So let's create a new float for the density. Paint density. And then get this, get the paint position, get the valid paint position as well. And our, missing something. Yeah, our paint radius. So our paint position, that's easy one. We can just drag from here and set vector parameter value. It's called sphere center. And we can just convert from this vector into a linear color. Now the next one, for the density, set a scalar parameter value, call this one density, and we can just connect it from our variable. Let's also make this one, and yeah, only that one public. Now finally, for our paint radius, it's going to be another scalar, so set a scalar parameter value. But our radius right now is not a scale with the mesh, so let's get our mesh and get a scale, get the actor scale 3D. Now, because we are still uniformly scaling our meshes, we can just take one of these, divide our radius by that size, and connect it, and also rename this to radius. So quick recap. Oh, let's use our valid paint position to only paint when we can. So branch. So if we are trying to paint on a valid position, then we begin our draw canvas. We set our material properties, sphere center, density, and radius. Then we draw that material, and finally we end our draw canvas. So let's compile and see if this works. One thing I made off camera was assign a new variable called isPainting to events for the left mouse button press and release. Now, the other thing is on the event tick, after we update our traces, then if that variable is set to true, I'm just calling the paint volume. That's so I don't have to click the paint volume function from the parameters window every time. So now let's see if this works. And it's working. And I can hold the button and we have a sphere, a volume sphere that follows until it's outside of the volume. Great, but this just paints one tiny sphere. So what if we want to keep adding density to this volume? Before we do that, let's make sure that our parameters work. We can increase the radius, 6 should cover the entire volume, and then paint density, let's do 25. And there we have it. Perfect. Let's reset this, go back to our blueprint. And I want to change this material because, well, instead of setting this value, which we're doing here, what happens if we just add the value to something else? Like, for example, add the value to the current value on our render target. So let's do a sample texture. and also a texture object parameter, so we can change this render target later if we have to. We can set the default value to the render target that we created earlier, and then we just add this value. So let's apply and save, and see if we can now increase the density. Yep, we can paint. That's pretty cool. And you can make blobs of volume. So we've seen how to add density to our render targets, but not how to remove it. And we'll update our paint function to allow that in a moment, but for now, basically what it's gonna do is just input a negative density. Well, let's try that and put, I don't know, minus 25, and let's shoot a tiny trace sphere throughout this volume. Whoop. And now we have a tiny little hole. So you could use this technique to make something like the smoke grenades in the new Counter-Strike. So you could shoot bullets through the smoke like that, or just throw a big grenade next to the smoke to temporarily clear it, like that. And obviously in that game it's a bit more complicated, because they voxelize the entire space in order to allow the volumes to propagate. But at least you can create similar effects with this technique. Now let's update our paint volume function to allow erasing density. You might have noticed also that I was changing the radius directly without changing the parameter here on the parameter details, and that's because I bound increasing and decreasing it to the mouse wheel up and down events. And I did the same for the left bracket and right bracket for the increase and decrease density respectively. Now let's go to our paint volume function, and first we need a new input to know if we are trying to erase or not. So let's call this is erasing or erase mode. Now we will want to branch from this, and let's make some room before we set the density on our material. So let's move all of this a little bit to the left. So if we are erasing, then let's do first, if we are not erasing, we just paint our density as usual. Now if we are erasing, we need to multiply this value by -1. So paint density multiply by -1. And then it goes back to radius, draw material, and draw canvas. Perfect. Let's compile. We don't get any errors. Save. And go back to our event graph, where we're going to need another boolean for is erasing now. It's erasing, and let's set this on the right mouse button. So on press, we'll set this to true, and on release, we'll set this to false. And finally, we'll check if it's not painting, then we'll take the value or check the value of is erasing, and we'll also branch. And we're doing it this way on the false output of this, or the false output of this this branch, because we don't want to paint and erase at the same time. So if it's not painting, then we check if it's erasing. And if that is true, then we paint on erase mode. everything seems correct. Let's compile and save and see if everything is working. And if everything is working, I should be able to add density with the left mouse button, something like that. Actually, let's try to make an adorable little skull. And then I could remove density with the right mouse button. Increase the density. And make a couple nostril holes. There we have it. Our little skull cloud. Next, let's add a little bit of noise to our paint material function so we can improve the appearance of these volumes. Later on, we're going to implement noise in our raymarching material, but for now, let's do it in our painter one. So we'll need a texture, so let's get a volume sample. So search for volume sample and pick the texture sample parameter volume node. This will need a name. We can call this one noise texture, maybe. And since it's a volume texture, it will need a vector 3 as coordinates. And thankfully, we are converting our UV coordinates to a vector 3 here. So we can just take this value and plug it in directly. Now let's choose a different texture than the default volume texture. We can search for Whirly. And if you enable the volumetrics plugin, you will find this texture there called Perlin Whirly Balanced, and it's a volume texture. Let's select it up and let's open it for a moment to see what we're dealing with. So we have this colorful sprite sheet representation of a volume texture, and it looks a bit messy, but if we take a look at the different components RGBA, we can see that each channel is a different scale of the same noise, which is a mix of Perlin and Whirly. So here we have these big, smooth, blobby shapes, and if we go across the different channels, we see the texture in different scales. So that was green, then blue, and finally the alpha with the smallest detail. Cool. Now we'll need a scalar parameter to control how much noise we are applying into our brush. So let's add that, call it noise amount. Now pick one of the channels from the texture. I think I'm going to just start with the red. And let's multiply this by our parameter. And maybe give this a default value of 1. Now we are generating this sphere mask that we're using as our brush, and we are multiplying it by the density. So before we do that, let's subtract from that value our noise sample. So add a subtract, and from that noise, or from that sphere mask, we're subtracting the scaled noise value. Now we don't want these values to go below 0 before we apply our density scale. So let's add another maximum between that value and 0. Hit next, and then connect it to the density multiplier, and then keep the same. And now we can see immediately that our perfectly smooth sphere, it's very noisy, and it kind of looks like clouds. Let's take a look and see if that worked. So let's try painting it now, and it works, and we're making these adorable puffy little clouds. That's great. And removing density still works fine, and it's also using this noise, so we can create a lot of interesting shapes. And let's try modifying the parameters, or the parameter. So we set it back to 0 noise amount. We should have, yep, perfectly smooth spheres, and let's do 0.5. and we have a bit of noise. Excellent. Now the different channels, let's set back to 1 and try the red one. Let's do a line maybe like that, and then let's change the channel output for the green one and hit apply and save and try again. Then the blue one, and finally the alpha channel. And as we can see, the different channels have a very drastic effect on the output that we get from the mask, which I think it's pretty cool. We can then erase with a different one. So the best way to use this probably would be to combine some of these effects together. So for example, doing something like the red channel times half of the green channel, or some other combination like that. Or even better, you could have different parameters to allow the user to control the amount of noise of every different scale. And for the rest of this example, I'm going just to keep it as the green one. I think that's a good mix. But last thing I want to do on this volume painter material is change it so we don't apply this noise to the entire sphere mask. So if you remember, our saturate here is giving us this perfect sphere that then we are applying all this noise to. So we can take the inverse of that with a 1 minus and then multiply this by our noise. So let's multiply this by 1 minus saturate and then reconnect it to the subtract. And now our noise is applied completely on the edges, and as it gets closer to the center of the sphere, the noise disappears, which I think offers a little bit of a better result. So let's give this a try, clear the canvas, and yeah, I think this looks a lot better. Again, if you made it this far, you can probably make a better editor than this. And next, we're going to make some tweaks on our volumetric raymarcher material, so it also has noise, but more importantly, animation. Let's bring it up. And we'll start by adding a couple of new inputs to our function. So add 2 new inputs for a total of 23. And the first one is going to be our noise texture, so noise text, and the second one a noise offset. This value is going to be based on time, and we could calculate that inside our function, but it will be a bit more efficient if we do those operations outside of our for loops. So let's give them some values. For noise texture, we're going to grab an object, a texture object. There we go. And select our Perlin Worley volume. So the volume version of this texture. We can connect that directly to our noise texture. And for our noise offset, let's start by taking the time and scaling that by a factor. Multiply by a new scalar. We can call this time scale. Set to 1 for now. And we're going to multiply that again by a vector. Vector parameter that we can call noise direction. And then let's connect this to our noise offset. Hit and apply, and we'll need to make a couple changes in our code. Let me write those in a WordPad session, and I'll be right back. And here we have it. As you can see, there's only 2 new lines to add. In the first one, we're going to sample our volume texture which is here, using this function called texture3dSample. Now this also requires a sampler and a position to sample, which in this case is our current position, this is in our raymarching algorithm, plus the noise offset parameter that we pass to the function. Next, we are updating the current sample, which is the density that we sample in our volume, by subtracting the maximum of this value and 0, just to make sure that this value doesn't go into negatives. And in this case, I'm using the green channel multiplied by the negative or the inverse, so 1 minus the current sample. Now, if you want to scale the noise texture, which we could have passed as a parameter, but here I'm going to add just a constant, maybe 5, or maybe 4. Repeat it 4 times. And if you want to increase the effect of this noise, or how deep into the density it penetrates, we can increase this value. So instead of 1 minus the current sample, we could do something like 5 minus the current sample. Again, both of these numbers could be parameters passed to the function. So just copy this and let's paste it in our code. Now we want to paste this after we take the sample and before we do everything else in our raymarching algorithm. Just paste these 2 lines and immediately we have a lot less density, which seems promising. Now we can apply and save, and let's also change the noise direction default value. So maybe -1 on the Z axis, so it moves vertically. So now let's hit apply and save, and there we have it. Now our noise has a really cool animation effect. Another way to animate this would be to transform the density over time. Right now we have a fixed density, and when we render it, we are just applying this noise. So as you can see, this noise pattern cycles over time. If we wanted to do something like this actual density fading away and flowing through the map, we would need to do something very similar to our volume painter material here. So in this material, we are taking the render target volume and adding whatever our brush parameters say that we have to add. But we could easily create a function or a new material called fade out, for example, that took the render target, sampled it, and then multiplied it by a value of less than 1. And that would eventually fade this texture out. And if you want to do something more complicated, you could sample the render target volume, do a fluid motion or Brownian motion type of pass, and then output it again. And I won't do that for this tutorial because I think it's already pretty long, but I made already a tutorial on material passes and fluid approximations before, so feel free to check that one out if you want to try it out here. And that's gonna mark the end of this video, and at least for now, this tutorial series. I hope that you've had fun and learned some new things about volumetric rendering. If you still have questions though, or suggestions about topics for me to tackle next, feel free to leave a comment below. And if you like this content and want to see more stuff like this, please consider subscribing to the channel. See you next time!